Good morning, everybody. My name is Justin Reifus. I'm a verification engineer for NVIDIA, working on methodology. And today I'm going to be talking on behalf of the Accellera working group, on which I'm the vice chair, for UVM reference implementation development, talking a little bit about UVM, about the IEEE 1800.2, which is also UVM, and talking about moving forward with it. Okay, so the agenda today. We're going to talk about why we want to migrate everyone's library forward, what are the benefits of that, some of the ways that we hope to improve interactions with the community in general, and also talking about the future of UVM. But we can't really talk about the future without talking about the present. So looking out, we're a pretty good-sized group, considering we're not talking about ML or deep learning or any of that. So let's just do a quick show of hands. Who here is actively using UVM today? Good. I was hoping to see that. Okay. Now, keep them up. Keep them up. All right. Lazy buggers. All right. Who here is actively using 1800.2? Now, that could be anything from 2017 forward for UVM. Therein lies the problem. Okay. How many people are using 1.2? Okay, good. You're not ancient. It's old, but it's not ancient. 1.1. Come on, guys. Really? Wait. 1.1, and it's not because you have to be compatible with somebody else's stuff. Oh, come on, you. All right. So really, the purpose of this presentation is to help everybody understand how to move forward from the sometimes ancient, sometimes just very old versions of the library, and the things that we've done to kind of grease the skids there and make life a little bit easier. So why bother switching to this latest version of the library? The latest version of the library has a bunch of things added to it. But in the past, it's always been kind of a cost-benefit analysis, as engineering always is. The cost of moving to 1800.2 was very steep. All right? You had any of the stuff that was deprecated in 1.1, any of the stuff deprecated in 1.2, then you have the new versions of things that are coming in, and why would we even do that? What's the purpose in changing just for the sake of change? The Accellera working group heard you. We heard you, 4 years ago. We heard you 3 years ago, 2 years ago. Some of you have been very vocal over the last year. We know that cost-benefit analysis was a little bit tweaked once the 1800.2 reference implementation came out. However, we have done a lot of work to kind of rebalance those scales. So today I'm going to be talking about many of the performance enhancements that are going in, many of the functional enhancements that have gone into the 1800.2 reference implementation, the bug fixes, and that last one actually kind of falls under functional enhancements, but what I'll call that is interoperability that we've done. That depending on exactly how complicated your test bench is, depending on exactly what you're doing, it might be a lot easier to do it now. But the one on your right is significantly where the chunk of our work has really been going into. We have been doing absolutely everything possible to lower the number of roadblocks when transitioning your version from 1.2 to 1800.2. Now, why are there roadblocks at all? Part of it, I'm going to blame on System Verilog. We all know and love System Verilog. There is no language better than System Verilog. You will never need a language other than System Verilog to do what you're doing. I couldn't tell if that was laughter or coughing. The big thing with System Verilog is that System Verilog doesn't allow you to have function overloading. So the System C guys, they get to do this the easy way. They come up with a new version of the LRM, and their function arguments changed. Oh well, just make a new function with the same exact name, and the compiler can figure it out. In Verilog, we don't get to do that. Once the function and its arguments, the signature has been set down, it either stays that way and you're backwards compatible, or it changes and you're not backwards compatible. And what we have here is a little Venn diagram. It's way blown out of proportion for the purposes of the slide. In reality, those circles are almost entirely covering each other. But the intention is to show that the 1800.2 reference implementation, which is released by the Accellera UVM working group, that implementation has to be written to 1800.2. It has to be written to the standard. We're not allowed to deviate from the standard. We're certainly not allowed to say that the standard got it wrong when it changed something. And when we do that, sometimes that means that we have to walk away from things that were in the previous version of the library, which is where all of our backwards incompatibilities come from. Now, when the IEEE finally ratified 1800.2, this was back in 2016, 2017, the Accellera working group had a choice. And I will stand up here, I will take the slings and arrows, and I will apologize because in hindsight, I'll say we made the wrong choice. The choice was, what do we do with things where backwards compatibility is not strongly called out? All right? We broke it down here. There's basically three categories of things that are incompatible between 1800.2 and 1.2. The first category, the largest category, is cosmetic changes. And I'll get into what each and every one of these categories is, but that's the ruling majority of our changes. Now, when we say that there are 35 cosmetic issues, it's important to note that one issue might cover a whole swath of APIs. I mean, you could really be up in the hundreds of APIs in those 35 issues. The next group, which is smaller, is the safety group. And these are things where we made a change. It isn't really a cosmetic change. It does have some functional reason for it, and it was primarily to prevent bugs. That's why we made those changes. And then the final group is the group that we're going to call strict compliance. So those are our three major sections, and realistically, any backwards incompatibility between 1.2 and 1800.2, a la 2017, falls into those groups. So let's take a look at that first group. The first group is cosmetic. This is my favorite example. This is an example that people complained about almost immediately. And it's such a simple example, because if we look, UVM do with. Who here uses that macro or some version of that macro? Okay, enough. Incredibly commonly used. All right, you pass in the item, you pass in the sequencer, you pass in the constraint. It exists in 1.2 along with UVM do on, UVM do with on, UVM do pry. There's 12 or 14 of these macros that go together, and in the LRM, or the language reference manual for 1800.2, we basically said, that's a whole lot of text that we don't want. It was like 20 pages of text, all describing the same thing over and over and over again. So we compressed it all into UVM do. Now the difference between 1800.2 and 1.2 is that 1.2 basically, you wind the clock back, comes from OVM, System Verilog 3.1, way old. It didn't have macros with default values. 1800.2 was written against whatever the LRM was in 2016. So we do have default values. So we went and we said, okay, well, really, there's just one macro, and it's got the priority with a default value, and it's got the constraint with a default value. And now, instead of having 20 pages of LRM, we have one. Yes, we saved paper in a world where everyone uses a PDF. We're sorry. All of that has been re-added back into the reference implementation. We should not have done anything. For what it's worth, we didn't strictly remove the old macros. We just put them over into a deprecated folder, and you would still get them by default. You didn't have to do anything. But those are the types of changes that we're talking about when we say that these are just cosmetic changes. The LRM, the LRM is what it is, but there was no reason the reference implementation needed to take that hit. So we added all of those back in. You don't need to set any flags to get them. You don't need any special compilation options or anything like that. They're back in. Are they going to go into the 1800.2 standard? Probably not. They don't need to. There would be nothing improved in the standard by having them available. But then again, if somebody were to scream loudly enough, there's no reason not to put them in. It's just a matter of saving text. So those are the cosmetic changes. That entire first column, all 35 issues, gone. One pull request. Safety. This one's a little bit more important. All right. For safety, you've got, in 1.2, you had the UVM default printer. In 1800.2, we changed it. Does anybody know why we changed it? Anything? Okay. That UVM default printer is statically initialized. All right. If you happen to statically initialize your code and you try and use the default printer, there's all the possibility in the world it's going to be null. And you're going to get a weird runtime error, because everybody loves runtime as opposed to compile time. And you're going to have to debug it. You're going to have static races in your code. You're going to have to debug those, all sorts of fun things that you don't want to deal with. In 1800.2, this was changed. And now, instead of being a static variable, it's a static method, with the rule being that the static method cannot return null. So you are guaranteed, no matter when you call that, even if you call it before UVM has initialized, UVM will initialize for you in order to get that variable to return a good value. This, like I said, it's a safety thing, but it is kind of annoying, though. We went from a one-liner to a two-liner. Man, if somebody would fix that. System Verilog 2023 comes in. All right. One-liner, because Systems Verilog 2023 gives you, it doesn't call it function chaining. I forget exactly what we ended on. It was something about implicit variables, something like that. But one-liner replacement. Old way, new way. Unsafe way, more safe way. I say more safe because get default, you would think like, oh, well, what if that returns null? I might get a null pointer dereference. It's specified as never returning null. All right, it's always going to give you something. But that's a change in the code, which means that your code in 1.2 is incompatible with the 1800.2 library. Now, it's a good reason, right? Safety. We wanted to save you from bugs, but in the process, we introduced compile failures, which are arguably better, but not in this case. So we re-added all of these items. When we did the get default, we made a local variable buried somewhere in the UVM printer, I think, and you couldn't access it by default. Well, listen, we could have just kept the old variable. All right, just don't document it. Nobody needs to know it exists, except for the people who are already using it. And the new way can just return that variable. There was no reason that we had to make your code fail. We were trying to help, but road to hell and all of that. So all of those items have been re-added. Please be careful with your code. Know that we changed these things for a reason. The code is dangerous. You should be using the new APIs. However, compatibility is paramount. And that brings us to the kind of most important change that we've done for the implementation in general. It used to be that the library was not only your reference implementation, but to some degree it was also enforcing compliance. If you were using an API that was deprecated, that's great. However, we provided a flag that you could pass in to the library that said UVM no deprecated. And all of those deprecated APIs would go away. And then you would know, oh, okay, your code is compliant. You are compliant to this version of the reference implementation, which is great because your compile would fail if you weren't compliant. Not so great because you're intentionally taking away backwards compatibility. The issue there is it's difficult to maintain that flag, the no deprecated flag, because these things tend to kind of interweave with each other, and you get APIs that accidentally kind of sort of depend on each other. And what the working group did when we moved to 1800.2 is we said, okay, this is a clean break. Right? We've elevated ourselves to being a IEEE standard. We are the reference implementation of an IEEE standard. Now is the time to burn that bridge. That's the mea culpa. That's the thing that in hindsight really hurt us more than it helped us. Today, not only are we not doing that, we put those things back in, we don't even have the no deprecated flag anymore. We're not even giving you that option. The working group is getting out of the game of compliance. We are in the game of compatibility. We are giving you the reference implementation written to the 1800.2 standard, and as much as possible, we're going to bring the old ships with us. If you want compliance, we have put as comments into the reference implementation to enumerate the different APIs so that a linting tool can tell you, oh, you're using the compatibility APIs. You're using something that is Accellera specific, because there are things that we put into the library that have nothing to do with what the standard says. Most of these have to do with debug and, like phase tracing and all of that. Incredibly useful. The standard says nothing about that. So that's an Accellera API. And then we mark all of the ones that we threw in just for compatibility purposes. And this is great because it allows the linting tools to go in and they can tell you if, oh, well, you are using a compatibility API, here's the official API that maybe you should be using. Basically, from an Accellera working group's perspective, strict compliance is not our problem. That is not why we're there. So with all of that, if we take all of those cosmetic changes and we knock them all down, we take those safety changes, please write safe code, we knock them all down. That leaves us with this little white sliver. And anything that is not in the white sliver, you don't need to change your code at all. If it runs in 1.2 and it falls into that blue area, it runs in 1800.2. Congrats. Reference implementation, not compliance. That's not the game we're playing. But there is still an unshaded area, and that is necessary LRM compliance. So what does necessary LRM compliance look like? This is my personal favorite because it burned almost every single test bench that I touched. UVM report server was changed. In the olden days, it was just a single class. In 1800.2, it was split up using good software practices, patterns. We split up the implementation from the interface, not an interface class, but UVM report server in the old days was both the implementation and your base class. You could extend it, do whatever you wanted to do, and everything would just work. In the new days, UVM report server is the base class. Default report server is the implementation, which means in order to have your code function, in the olden days, you extended the one, and in the new days, you extend the other. This is painful. This is a code change that you would have to maintain. These are the things that really hurt. Now, as I said, there aren't a lot of these, but they definitely exist. So how do we deal with these? Because ideally, I want my code to work in 1800.2 and in 1.2. And like I said, we're not allowed to change them. The Accellera reference implementation can't go in and be like, oh, those IEEE guys, which, by the way, take the UVM working group from Accellera, take their hats off, put an IEEE hat on them. It's the same people. And we even used the same WebEx for a while. Technically speaking, different groups, different priorities, but same people. All right, so we can't just ignore what 1800.2 says. Is there anything Accellera can do to make this easier? Well, there's an if-def, because we all love if-defs. I mean, who here doesn't love an if-def? Technically speaking, that UVM version macro only exists in 1800.2. It doesn't seem like it would. It seems like that would be something that existed in the old days, but no, that one's new. And so that's what we can use to detect that you are in 1800.2. If that macro exists, you're there. If it doesn't exist, you're in 1.2 or earlier. So we can write an if-def. And now our code works. It is compatible with 1.2, and it's compatible with 1800.2. Nothing could be better. I'm going to sit down. Presentation's over. No, we got to be able to beat that. All right. I give you the UVM compatibility package. Accellera realized we can't change it, but there's got to be a better way than littering people's codes with a bunch of if-defs. Accellera is now releasing, in parallel to the 1800.2 reference implementation, another package called the UVM compatibility package. When I say in parallel, I mean directory structures. If you have your source directory, which has got UVM package.sv, parallel to the source directory, a common sibling, is the compat directory that has UVM compat package.sv. And the reason why we released it in parallel and not in the same directory is that compat package can compile against 1800.2 and it can compile against 1.2. The same compatibility package works with both of them, which means now user code can be modified, and like I said, this is a case where it's got to be modified. The two are functionally different. There's nothing we can do about that. But it can be modified in such a way that the code itself is no different when you're writing it. You write it to the compatibility package. The compatibility package worries about what does that mean in 1.2 versus what does that mean in 1800.2. So the example here is instead of extending from UVM report server or instead of extending from UVM default report server, you extend from the very shortly named UVM compat default report server. Again, there's only so much we can do within the English language, let alone system Verilog. But your code then doesn't need to change. After you put in the compatibility package, you have no further changes that you need to worry about. The package itself will deal with anything that needs to happen, and you'd be surprised. For this, it's a simple type def. And it basically in the compatibility package, we have the 5 lines that I showed you on this slide. For other things, it's significantly more code, not because the old way was better or the new way is better, but because something was changed, something was some underlying implementation aspect was changed. But all of that is just buried inside of the compatibility package specifically to get it out of your hair. And so with the compatibility package, I really wanted to use a Band-Aid as opposed to another circle, but I was outvoted on that one. With the compatibility package, you do have a small amount of code modification. That code modification can be tested against your existing code line. It doesn't require you to move forward to 1800.2. You can keep everything in 1.2 while you're getting your code into place for the compatibility package, and only after that would you move forward. But I don't know how good your eyesight is. That circle's not quite covering the entirety of the white sliver there. We still have everybody's best friend, corner cases. So what do we mean by corner cases? These are things where no one's going to judge you for it, but you all went into our code and looked at what we were doing without asking. No, it's all undocumented APIs. Stuff that there was no way to do anything without going into these undocumented APIs. MROs, if anyone's ever created their own printer and they didn't access MROs, good on you. I mean, you did what you were technically supposed to do, but holy cow, is that a lot of work. Get local map and get default map, there was just no way to do that in 1.2. You needed to use those undocumented APIs. And the UVM print macros, those are fun. They were never intended for public consumption, and yet somehow everybody learned about them. They were like inside the deep, dark arts of how the UVM field macros worked. But never intended for public use, and there's no great way to fix that problem. That said, the UVM print macros, we have the compatibility package now, supports those. So that one goes off the list. MROs, there is an open bug against the compatibility package. We think we can get that one in too. And get local map, get default map, Again, the compatibility package is probably going to be able to hide that from you. So even though these are 3 examples of things that we know have burned people within the last year, keep your eyes on that compatibility package. Those issues are probably going away. Okay, so that's the end of kind of what have we done to grease the skids and make it easier for you to switch to 1800.2 in an attempt to kind of, sand down those roadblocks and make it as easy as possible. But what we didn't do is answer the question of why. Why should we move forward to 1800.2? Obviously, everyone wants to be on the bleeding edge of everything when you're verifying chips that take years to make and where the cost of a bug is millions of dollars. You want to be bleeding edge. That's what you want. No. The reasons for moving forward to 1800.2 fall into a couple of categories. The big ones are performance and functionality. So performance. All of these performance enhancements, and I'll go through and you'll be able to figure out for yourselves whether or not these apply to you, but all of them have been applied since 2017. A quick aside here, because at some point in time around the 1800.2 switch, versioning numbers got really confusing. People were wondering, why did we go back to 1.0? We didn't go back to 1.0. The major number is the year. So we went from 1.2 to 2017.0.9. So from 1 to 2017, not from 1 to 0. But yeah, those are the version numbers and the various enhancements that were put in. And I'll go through them here kind of actually in a reverse order. Most recent first. Register blocks. Don't know if people here are using RAL, everybody's favorite part of UVM, known for its performance and speed. We have added a cache system to the UVM RAL model. Very simple cache system, has to do with how, find blocks, find reg, how all of those work and all the string-based mechanisms to kind of iteratively go through. And once you find a given block or model, whatever it is that you're trying to pull, if you were to ask again, we didn't cache the result. So we would go through and do all of that work again. Nowadays, we're caching. It's a nice, simple enhancement. It can be turned on via a runtime plus arg. You might be wondering, why not just always have this enhancement turned on? There are members of the community that have RAW models that are massive. And if we simply turned on the cache for all of their model all the time, their memory usage would explode. And so they wanted to continue to have the kind of perf hit for CPU efficiency as opposed to needing to, rededicate new machines in the farm. But, under the average use case, turning on this reg lookup cache is pretty darn good. We also added a new API that is even more of a cache, and it is to pull registers, fields, blocks by their full name. We build this when you lock the model. This one is a massive perf improvement. The team that provided this patch to the reference implementation, forgive me, I don't recall if they said it was a 9x improvement or a 90% improvement. Either way, that's a big number. So this one works exactly the same way in that it's just a cache on the back end, and it just builds it all into basically an associative array. So now looking up anything is lightning fast. And between the two of those, I'm not going to say RAL is fast now. RAL has never been fast. I think RAL being moderate is pretty freaking good. So we're closer to moderate. The next big area of improvement, and this one has been around for a long, long time, is apply config settings. So I'm going to ask you to raise your hands again here in a second. Just get your arms warmed up. Who here has been told do not use the field macros? 99% of the time, this is why. Okay, if you use the field macros inside of a component, you trigger this mechanism called apply config settings. And what apply config settings is doing is it's going into the config database, trying to figure out whether or not you used the config database to set those macros. Now, for UVM objects, it's not a problem. They don't have apply config settings. But for components, it can be incredibly painful. So even if you weren't using the field macros, some sources said, oh, okay, well, the way to really avoid the pain of this is to not call super.build, which is true. If you do not call super.build, you will not get apply config settings. But depending on what component you're in, if you don't call super.build, you might not also get what that component's supposed to do. So that isn't really a great answer. We knew about that in 1.2. We fixed it, quote unquote, in 1800.2 by adding this new method. All components have this useAutomaticConfig virtual method. It's called automatically during construction. And if it returns 0, we're not going to call apply config settings. That's all it does. So instead of don't call super.build, it's return 0 in that function. If you want, you can have a base class that can do this. You can use the mixin that does this. There's a million and one ways to skin that cat. But all you got to do, return 0. We won't call apply config settings. The TLM ports, which Cliff was asking about before, TLM in UVM is a fun implementation. If you are ever incredibly bored and want something to make you sad, go and read the implementation of TLM and see how it does what it does. One of the nasty little secrets is that every single one of your TLM ports is in and of itself a component, or actually has a component inside of it. And all of those components would have apply config settings. So everything in TLM has this return 0 automatically. So all your TLM stuff went a little bit faster when you moved to 2017. But this particular issue of config settings in the config DB, this is the gift that keeps on giving. In apply config settings, the way that the standard says that we have to do it is the component is going to look in the config database and find every field that matches that component's scope and apply those fields via apply config settings. Let's just think about that. You have the entire resource database. You have all that stuff that you had to put in to make RAL not spew huge amounts of information for no reason. All of those, I don't want to run this bit bash test, like all those things have to be in there. And every single component is going to look at every single field and see if its scope matches any resource that has been set with that field. It might as well just be called punish my simulation, please. It wasn't as painful in the OVM days. This kind of was when we refactored the config DB and the resource DB to make them more useful in general. We just kind of missed a part of the game there. So what we do now in the reference implementation is we said, okay, we're only going to do that if you declared a field. Like if you declared that you had a field. Now we're going to go and look for that field. Okay, we're not going to look for everything. That's just incredibly painful and for no good reason. Technically speaking, though, we're violating the LRM. So this flag here, it is a compile time define. You got to turn it on. Tells us, no, you got to go in strict mode by default. And in strict mode, that's the one where we basically should have called it punish my apply config settings, please. But config strict means, okay, you got to do what the LRM tells us to do. This is a case where we put in an API that allows us to ignore the LRM based on configuration, kind of ironically, and we defaulted to ignoring the LRM. We did it because nobody on the working group had a single use case where they said the old way was better. So we were willing to say, okay, we're going to, next time the IEEE spins up, we will get the LRM changed in this language to support this new API out of the box. And that way we are backward compatible with everybody. Anybody who used that very strange functionality, their code will still work, but it will allow the reference implementation to go faster. That one's big. But between this one and this one, you have a very large chunk of your build time performance hits are gone. All right, so that brings us to the last one, which is, again, a build time performance hit, and that is regular expressions. So regular expressions are incredibly inefficient because you have to build them, And when you build them, that's, you're crossing over into the C boundary using DPI. We have to parse the string and build it. And thank goodness the standard library does that for us. And we do all that work, and then we do your comparison. And then we free the memory of the regular expression, and we return from DPI. That's a whole lot of waste right there, because it turns out, like I said in the previous slide, many components are going to check themselves against the same scope or against the same regular expression. So why the heck are we recompiling this thing? That's the most costly part of the regex is the compilation and the memory allocation for the compilation. So we started caching that. This is another one where you got to turn it on. The main reason for turning it on in this case is not memory explosion. The caching is done in such a way that it prevents itself from consuming too much memory. But if the vendor solution for save and restore, depending on exactly how it's implemented by the vendor, it may or may not work out of the box with this enhancement. And there's a big rule where we try not to release anything that breaks everyone's code. So we made it so that it's an opt-in, compile time opt-in, to enable that cache. Okay, functional enhancements. Things that were added into the reference implementation to make life better. I'm going to go through them really, really quickly, okay? The first one, caches. We just talked about them for the RAL model, and we talked about them for regular expressions. There is a base class, which is just a simple API. The cache has the ability to look up keys and eviction capabilities. All of it's documented in the release notes and in the HTML. I'm not going to dig too deep into it. But basically, these things are useful anytime you have something that costs a lot to make. An example for the regular expressions is the regular expression. It costs a lot to compile that, but it doesn't cost a lot to use it. So we keep a certain number of them. In SV23, again, something was added called a weak reference. Weak reference is, everybody knows how in System Verilog, you don't really need to worry about memory management. So long as somebody's got a reference to a handle, that thing will stay loaded in memory. When nobody has a reference to it anymore, that thing will get removed from memory. Weak references allow you to say, I don't want to keep this thing in memory. I just want to know when no one's using it. And when no one's using it, then I can react. And so recommend going and giving that portion of the spec a read, not because I wrote it, but because it is excellent just for its own sake. But combined with caches, that is incredibly powerful. Like I said, this is used internally for the regex optimization. And so here's just kind of a simple example of how they work. That very top item, UVM shared, that is my personal favorite 3 lines of code in all of UVM. It is class UVM shared with type parameter t, declares a variable of t, and class. That's all it is. But it acts as a shared pointer, which is really, really powerful. So in this case, we're going to use it for a bit stream. Bit stream is 4K. The shared pointer is effectively 64 bits worth of reference. And now you can put that bit stream in the cache. Whoever needs to use it can use it. And when we evict it from the cache, we don't actually need to get rid of the bit stream. We can keep it. And the next person who needs a bit stream can use that 4K. So that's what you can do with a cache and UVM shared or something like it, where you can keep around these things that are kind of costly to maintain or costly to create. And then the actual usage of the cache looks very much so like interacting with an associative array. You can see that on the second line of the example, mycache.get, and it's returning that optional data. That's a syntax sugar. It does the same thing that System Verilog does when you use like find. Find doesn't return the index, it returns a queue of the index. If the queue has a value in it, then it found it. If the queue is empty, then it didn't find it. Same thing, we just call it optional data to make it a little bit easier to read. And so, we get the key, we check the size. If it's there, we found it, great. If it isn't there, then we're going to put it in. Caching, not a new concept in software, but it's now built into UVM very efficiently and very extensively. Process guards. This is I love this one. This is my personal favorite. I don't know if anybody here has been hit by this particular bug, but you have a driver, usually a register-related driver, that is performing some operation, and then all of a sudden, the driver's not doing anything. And you go back and you look and you say, why isn't the driver doing anything? And after a lot of debug, it turns out that somebody disabled a fork, or they did a process.kill that had a sequence in it. And so that sequence just kind of and died without kill getting called, without any messages, nobody recovered, nothing could be done. It's just a dead process in system Verilog. I hate debugging these things. Process guards are a new mechanism that allow you to detect when your process has been unexpectedly terminated. And then you can react accordingly. Sometimes that reaction is just to say, oh, this is an error. Nobody can recover from this. Sometimes it is a completely recoverable process. So here's just kind of an example of that one. You have your UVM sequence. It declares a process guard. You'll note that the process guard is parameterized with the sequence type. That's because it's going to call this process guard triggered if it fails. In the body, it instances the process guard. That's it. You instanced it, you're guarded. If your process dies before that guard is cleared, we're going to call process guard triggered. It doesn't matter if you are killed immediately after that construction or 5 nanoseconds after that construction. If clear is not called, that method is going to trigger. And so in this case, we're going to detect, oh, somebody killed my process. I'm going to call sequence.kill on myself, and my sequence can clear out and react appropriately. You might look at that and say, well, that's generically useful. Like, I kind of wish all of my sequences did that. Good news, they do. We put it in. So now, if any sequence is unexpectedly terminated because somebody did a stray process.kill or a disable fork or pick your other poison for bad ways to kill things, your sequence will now get its kill triggered. In RAL, if a read or a write gets killed unexpectedly, at the moment, I believe you'll get an error. We're working on it so that it's actually recoverable. It will become a warning that then your test bench can just react to. The fact that, oh, the register is in a bad state. We need to get it back into a good state. Next up, this is the only one of these that's experimental. And this is kind of a common problem, I gotta be honest. After 20 years, 20 plus if you include OVM, I'm kind of surprised this one still exists. But it's an attempt at the answer to what do we do with signals that aren't transactional? You know, I've got a 3-pin interrupt. You know, halfway through my DUT, I just want to know when the thing changes. I don't want a monitor and an object and a yada, 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 yada. I just want to know when that pin changed. That's what the polling mechanism is for. It's similar in nature to RAL with the front door and the back door. It provides a PLI-based backdoor, which is going to slow down your simulation. So if you're going to do this, use the front door, and you have to implement it using you can use a virtual interface if you want. You can use classes if you want. It's really up to you. But it allows you to say these signals exist for anybody who wants to interact with them. And now the test bench can interact by string. It doesn't need to have explicit out-of-module references or any connections like that. It's handled by this API. Like I said, this API is experimental. We want people to use it. We want feedback on it. We know it's not perfect. But it's at a state where feedback would be a good thing. And that brings me to that last category, that compatibility category that I talked about, which are the functional layering enhancements. Functional layering is intended to remove the need for you and your tool providers and your vendors and everybody else to stop messing with our library. We wrote it, you don't get to write it, that's just rude. No, the intention is to make it so that we don't all have to modify the library anymore. The common cases I can think of here, most vendors, I don't know if it's every vendor, but a lot of vendors provide their own version of the UVM library. Yay. There is a tool set for mixed language, UVM-ML. that provides a modified version of the UVM library. Depending on how infrastructure works at your company, you might have your own version of the UVM library. I can tell you at NVIDIA, at one point, we had 8 versions of the UVM, all 1.2. 8 different versions. So the functional layering is intended to lower the need for that. And there's 3 big areas that I'll cover today. The first one has to do with RAL, once again, our best friend. When a RAL check fails, wouldn't you like to be able to add any debug information you wanted into that scenario? Like, okay, by default, the model is going to tell you, hey, for this register and this field, we expected to see foo and we saw bar. That's what it's going to tell you. But now we have the register error service that you can set. It's just a factory override. And allows you to actually react to the fact that that check failed. You have access to the register, the expected value, the actual value, the map that the register was being accessed from, and the bits that we considered valid for that access. You can do absolutely anything you want to in there. It's yours. You will likely be able to come up with a much more useful error than ours. So RAL opened up with that. Resource DB layering. This is anybody who ever turned on config trace or resource DB tracing and said, wow, that's a whole lot of not useful information. Boy, I wish I could add more. That's how you do it. I can tell you we have a specific user in the working group where they just wanted to know who all was accessing the resource database, because shame on you, that's horribly inefficient, until we optimized the regexes. So they got in there and they were able to use this, and they just recorded every accessor. That's all they cared about, was just who was doing it. That way they could go and attack those specific components to reduce how often they were thrashing the database. So again, that can be done. Don't need to modify the UVM library at all to do that. The phase hopper, this one is similar for debug in that it allows you to get in every time something's going to happen in phasing. Again, I mean, there are so many parts of UVM that everybody loves. RAL, phasing, oh, come on. It's such a great library. But inside of phasing, you have the ability to get in before the phase is executed and react accordingly. So the use case here is, in the build phase, we wanted to know which components were taking the most time. Sensing a similar thread here. People want to know who's thrashing the resource database. Regular expressions want to be optimized. The build phase, we want to optimize. It's almost like we're all hitting this problem. So we were able to get in, and at NVIDIA, we just added just wall clock timer there. And just print, like, okay, we're inside of component foo. How long until it's done with its build phase? And from that, we could build a heat map. And from there, you're able to go in and optimize your test bench. That is a strictly debug use case. UVMML, on the other hand, they went in and they actually altered how phasing was occurring, because they're making it work with System C and Specman and other languages, and they needed to control how phasing was actually being executed. So they get in now and they can change that, so that they are controlling how phasing works. They didn't need to touch anything in the library to make that happen. So those 3 are just kind of the high order ones for this functional layering, this idea of we don't want anybody to have to modify the reference implementation. And if there's a bug, sure. But for functionality, no. We would really prefer that you were able to do everything you wanted to do using, effectively the tarball that's provided by Accellera. So, speaking of bugs, we never, ever release code with bugs. That does not happen. I don't know who told you that. They're a dirty liar. No, of course, the Accellera reference implementation has bugs. In fact, we have quite a few of them. This is just tracking just the IEEE releases. And looking at this, depending on whether you're an optimist or a pessimist, I like to look at this chart and I'm like, look at all those bugs we fixed. I mean, 2017 1.0, that's 55 bugs. It's worth noting that 1.2 was released 6 years prior. So 56 bugs. from that 6 years. And then 1.1, oh, we got a bunch of bugs after that. 1.0, ton of bugs after that. The 2020 releases, that was really aimed at a specific target, so you didn't really see many bugs come out of that. But once we got to 2.0, that's when all the backwards compatibility stuff comes in. It's like, oh man, this is great. We're fixing bugs on a daily basis. Until you look at it like this. And that's when we start applying time to it. All those bugs we knew about very early on. So the bugs in 2017 1.1, those 50 some odd bugs were opened almost immediately after 1.0. We knew about them, or they're older than 1.0. And it took us till then to get them released. And same thing with the bugs for 2.0 and 3.0. The main reason for that is that the working group is working on a cadence of we try not to release tarballs without having a major reason for doing it. Obviously, an IEEE release of the LRM is a major reason, but we also, some new feature or something is being added. That's when we release a new tarball. For bug fixes, we tend not to do that, but that's painful. Like I said, that 1.2 one, 6 years. We knew if we released 1.2 on January 1st, on January 2nd, we knew that there was a bug that would hit almost everybody who used UVM events, and we did nothing. I was not one of the chairs at the time. But bugs like that, we wanted to be able to get them out faster. So that's where the GitHub repo comes in. At GitHub, we are releasing patches to known bugs much faster now. So you can see the two red bars there added between 3.0 and 3.1. Between those two red bars, those are all of the functional bugs that we knew about between 3.0 and 3.1. If I were to extend this chart to Friday of this week, you would see another red bar. But the idea here is Accellera patches can now get out into the community that much faster. Because we're not doing full tarballs releases, we are releasing these patches into the Accellera official GitHub. And that's not a one-way street. We didn't do it just to get you bug fixes faster, although that's a hell of a thing. We also wanted to open the door to allow the user community to report issues directly to Accellera. There was no way to do that before. If you found a bug in UVM, if you're in the working group, great, you can open up a bug and we can get it fixed. If you're not in the working group, you gotta know a guy who's in the working group or talk to your rep. That was not an optimal way to make that work. So now you can go to that public repo in GitHub. You don't need an Accellera account or anything special, and you can open an issue there. We will reply to all issues. It's worth noting when it comes to actually addressing the issues, if it is a functional bug, the LRM says we shall do foo, but we do not, we will accept that issue and work on that issue. If it's an efficiency bug, a performance bug, wow, you guys could do this way faster and stay within the LRM, we will likely accept that issue as well. If it's, hey, I have this brand new idea for this thing that nobody's ever thought about and no one's ever talked about, and I think it should go into the UVM, those we will not accept. In order to get enhancements into the library, that has to go through the Accellera channels. So that's where it goes to either join the Accellera working group or your vendor is almost certainly on the Accellera working group and they can work with you that way. So that's kind of the purpose of the public repo. Like I said, we're pushing out bug fixes, patches, everything we can to make life easier for all the users, and we're hoping that the users can provide some feedback to what we're doing as well. On the topic of feedback, these are the things that the Accellera working group is looking at right now. Very high level. There's additional cleanup for 1800.2. We're talking about spinning up that working group again, just to kind of get, at this point it's been a few years, the reference implementation has added all that functional layering. It would be nice to get that into the official standard. It seems like every other week we talk about a RAL overhaul. It's very difficult to talk about RAL at the same time that we talk about backward compatibility, because the problems with RAL are foundational. It's designed in a way where it's very extensible, but in the process, it's going to consume a lot of memory. And you're going to have a lot of these, virtual methods calling virtual methods calling virtual methods. And we could fix that, but how do you do that and maintain backward compatibility? That's not really straightforward. That's not particularly easy. There's other performance improvements. While writing this slide deck, we opened 6 or 7 perf-related Mantis items, which bugs, and those will improve everybody's life. Everybody who's using 1800.2. If you're on 1.2, don't expect the perf to go up anytime soon. If you're on 1.1, same. And then finally, we're also focusing on the alignment with the other UVMs. I love the fact that we started with UVM, and then you've got UVM ML, UVM MS, UVM System C. CocoaDB has kind of a thing that it calls UVM. You've got UVM E. It kind of makes you wonder what that U stands for in UVM. Like everybody needs their own version of it. But we're working to make it so that these things can play nicely together as much as possible with the verification working group with System C. There's the UVM AMS group. There's the mixed language working group. And we're basically just trying to make sure that everybody, the left hand and the right hand, know what they're both doing. And then the final one, the question mark, and I told them when we made the slides, I was like, ooh, I get to throw mine in at the question mark because it's not on the slides. UVM's really big. Like anybody who's looked at the code base has seen it's big. It's got a lot of stuff in it. If we're going to fix RAL, to do it in a backward compatible way is almost impossible. It would be easier if we could just rip out RAL and have something else. And last year, there was a presentation how TLM is implemented horribly in UVM and how there's a better way to do it. And just because I was a co-author on that paper, I'm not going to sing its praises too high, but there are parts of UVM where we could fix them if we could get them out. If we could shrink the size of it, then we could potentially address these issues. So that's my personal top-level item is figuring out a way to take UVM and make it smaller. Because if we can make it smaller, first of all, there's less of a chance for bugs. But second of all, it's easier to fix things. It's easier to know exactly what I'm doing, exactly what I'm using, and exactly what I'm compatible with in that smaller world. That's what's on our plates at the moment, at the working group. It's possible you look at that and you're like, great, wonderful, can't wait, tell me when you did it. It's possible you look at that and you say, but what about blah, or this other thing? Tell us. Thank you very much.